So this is the second day for fair division, and let me begin by just giving some recap of what we did yesterday. So what we saw was fair division of divisible resources. And here the divisible resources, as you remember, we modeled it as a 0-1 interval or 0-1 segment, and okay. And also we just thought it of as a cake, and it can be land or anything, but yeah. So we've been talking about fair division of cake, and so to begin with, we also saw some notion of fairness, and the first one was proportionality. So okay, so can any one of you recall the definition of proportionality for me? Yeah. Let's say AI, just to be, okay. Yeah. Exactly. So this was proportionality. They are at least getting 1/n of the total value of the cake they have, and this happens for all agents in the set 1 to n. Okay, and I'm just denoting AI. Were we denoting it II as yesterday? Okay, let me just do that only. Okay, so this is proportionality, and the second notion which we saw was of NV freeness. So once again, can anyone recall the definition? Yeah, okay. NV freeness. So an allocation is said to be NV free if what happens? Vi of II? Yeah. Exactly. And this happens for all bundles J and for all agents. Basically this happens for all agents, and this particular inequality holds for every bundle for an agent I. Okay. So we also saw one particular thing about existence. So we know that an NV free allocation, okay, let me first talk about the connected cut. So in connected cut, what happens is everyone gets a single interval or a single segment. Let's say this goes to I3 and so on. So in this particular case, we saw that an NV-free solution always exists, and we saw it via Sperner's lemma, right? Remember at the end of yesterday we did Sperner's lemma, and so via Sperner, or which also, so we have existence result via two researchers, which is one is Sperner and other was Stromquist. So they both show existence of NV-free K-cut, a connected NV-free K-cut for all n. And then we also saw some algorithms. For proportionality to begin with, we saw one algorithm which in turn also gave existence, and it was moving knife algorithm or Dubious-Spanier algorithm, Dubious-Spanier moving knife. Okay. And then we moved on to NV freeness, and we kind of saw that it's not that tractable as is proportionality, and we saw for NV freeness, the very first algorithm we saw was what? Like for just two agents. Yeah, it was cut and choose protocol, right? So this was for n equal to 2, and then we saw for n equal to 3 also that we saw one NV free protocol, which was, yeah, okay, you might not remember the name, but it was, yeah, it was Selfridge-Conway. But yeah, this was in the disconnected setting. So this was for n equal to 3, and then we also saw, no, okay. We also talked about one result by Aziz and McKenzie, and this was for any n, and they basically showed a bounded, as in a finite and bounded protocol. But the only, I wouldn't say drawback, but the running time was the starkingly 6 stars of n to the power, n to the power, n to the power, n to the power n. So this was not, okay. So after this, we also talked about one particular algorithm, which was giving us one-third approximation, so one-third NV-free solution. And this was the, I think in the third lecture we saw this particular algorithm. So it's an approximation algorithm, but it runs in order NQ and also gives you connected cut. So it was a connected division. Yeah. Okay. So this was a quick recap of what we did yesterday. So what we'll be looking at today is, first of all, I'll just talk about the case of burnt cake to begin with. Okay. So I'll just mention what this model is, and we wouldn't go into the algorithms or the proofs or anything, but I just want to tell you there's one model which is being studied. So in this particular setting, what happens is, remember we had this particular assumption that Vi of any interval is, so we had this non-negativity assumption on the valuation functions of each agent, that they value any piece or any interval with a positive value. So this is a particular case when this particular assumption is not met. So this is not there, and you can have, so okay, so there's a bad cook or someone who just burnt the cake in the oven, and there are some portions of the cake which are now, let's say, negatively valued by some agent. There are pieces of positive valuation as well, but somewhere the cake is burnt or something like this is happening, and the agent really don't value it positively. So this is a case where you have positive and negative valuations over some segments of a cake. So again, so in this particular setting again, let's say we are again asking the same question, the same natural question, okay, does there exist an NV-free cake cut, NV-free cake division or cake cut? Let's say again for general n I'm asking, for general number of agents I mean, and again let me have connected pieces. Okay, so this is, so what do you think what happens here, like what can be the answer? Yeah, so you have bunch of negative valued pieces in the cake or in the segment 0, 1, and I'm again asking the same existential question to begin with, and the algorithms will come forward, but okay, we need to answer the existence question first. So in this particular case, it's a open area of research, and what is being shown, and it's a very recent result last year. So it's shown that okay, this becomes a little tricky, and we don't even know the existence for all n. What was shown was, to begin with, for n equal to 3, it was shown by I think Siegel Halevi, and then for n equal to 4, by which I mean when there are 4 agents or when it's prime. So this I think was shown by Munier. Yeah, this again is in 2018. So this is very recent area of research, and it was, so till now the existence of NV-free cake cut is just known for if it's n equal to 3, 4, or let's say prime number of agents in the system you are considering. We really don't know the existence for a general n yet, and it's still open. So can someone tell me, okay, let me move, but can someone tell me why can't I just apply Sperner's lemma or the construction which we did yesterday and show at least the existence to begin with? So okay, so remember in Sperner's lemma what we had was a triangulation. Okay, let me have some triangulation here, and okay, so the problem is I need to again come up with a Sperner labeling on these boundary vertices, right? So let's say this is, let's say labeled 1, 2, 3, okay, fine. But just, okay, so let me have this as 0, 2, 0, sorry, 0, 1, 0, and this is 1, 0, 0. So this, remember, these are the extremes of the cake, and this is other extreme, 0, 0, 3. Okay, so what do I want the labels on this particular edge for it to be a Sperner labeling? 1 or 2, right? Okay. But consider this, remember there was an ownership labeling and everything, but consider this, and there's an agent VA or VI, and let's say it has, let me draw it. Let's say the valuation function is somehow negative in some pieces. Yeah, okay. Let's say his valuation function is something like this. There is a big piece where he values the cake negatively, then there comes a positive cake as well, and then again he values the rest of the segment negatively. Let's say, I don't know, it can be any reason, but let's say it's burnt. So let me ask you, for this particular division, let's say this is some x, and let's say, so this division, let's say, is let's say, okay, let's say this division is x, but let's say this is x1 and this is x2. Okay, so I can represent it as x1, x2, and then 0, right? I just have two paths in this particular cut. So this particular point or this particular division will lie on this particular segment, right? Because the third coordinate is 0, right? It will definitely lie somewhere over here. But it's possible that valuation for this particular agent for, let's say, 0 to x1 is negative. And again, valuation for this particular agent, again for, let's say, x2 to 0, also sums up to be negative. But valuation of the 0th piece is 0, right? So if I'll go to that particular agent, let's say he's the owner of this particular vertex, and ask him, and this is this particular x, and I ask him, okay, what is the piece you prefer here? What do you think he will answer? Which piece does he prefer the most at this particular cut? 0, right? Which is the third piece, right? So as you can see, it may not be possible that we'll be able to always have a Sperner labeling, at least if we follow this particular proof, right? So the structure of Sperner's lemma breaks down, and therefore we cannot apply it, and therefore at least via this particular path we don't have existential proof, right? So in the case of burnt cake, when there's a mix of goods and bads, you don't have existence of NV freeness for all n yet. You do have for, let's say, these particular cases, and also existence over here are also shown by considering some generalizations of Sperner's lemma, and I will not go into those generalizations, but yeah, it's an open area of research and people are working on it. So any question in this thing? I just wanted to introduce this particular model so that you guys know that there's something out there. Okay. Okay. Yeah. Okay. So I'll move on to next thing if this is all clear to you. And okay, the thing I'll talk about is, so currently we had information about the valuations of all agents which was in the system, right? All n agents, let's say, right? So I in particular knew valuations for all agents, or in a way I was able to query every agent via Robertson web model. I was able to I was able to have cut and eval queries for, let's say, all the agents. But what we'll consider right now is partial information setting. Yeah. So the idea is, let's say there is one particular agent who is, I don't know, the boss or someone, and who really doesn't want to reveal his valuations, and he say he just, and let's say all others are in a situation to follow this particular thing, and so we have information about just n-1 agents and not all of them. And we say that the nth agent is being secretive. Let's say, consider another scenario. There is a birthday of a guy, or let's say a small boy, and he's the birthday boy, and we need to divide the cake again in n pieces. There are, let's say, n friends including him, and he just says that, okay, you guys do a division in n pieces, and since I'm a birthday boy, I'll just come at the end. Like a boss, I'll take one piece, and the remaining of n-1 friends will just divide the cake, let's say in envy-free manner. That's the goal of it. But yeah, so we give this particular liberty to, let's say, the birthday boy, since it's his birthday. So the setting is this: we have information, or we know the valuations of n-1 agents, and the last guy, or let's say the nth guy, is being secretive, which just means that I don't know anything about the valuation of nth agent. Okay. So in this particular partial information setting or secretive setting, we again have the question of existence and computation. Okay, what does it mean by exist? I'll be formal in a minute. Okay. So what does it mean by a secretive cut? Okay. Yeah. Okay, so what I need is, let's say I have n agents in the system, and nth guy is being, nth agent is secretive. So an allocation of the cake, which is 0, 1, an allocation, let's say I, so this particular allocation is said to be secretive, let's say envy free or proportional. We will look at both of the fairness notions, I mean. So I'll say that an allocation between, again, n agents is a secretive envy free allocation or secretive proportional allocation if something like this happens. If basically for every choice, okay, for every choice ik, there exists a bijection, let's say pi k. So informally what am I saying is, in this particular allocation, there are n pieces, and let's say the nth guy comes in and he picks, let's say, kth piece. So what I want is, for every piece picked up by the secretive agent, the remaining n-1 agents must be able to allocate the remaining n-1 pieces in a fair manner. Okay, so formally what I need is, for every choice ik, I need a bijection going from this set, the set of agents minus the particular agent n, because he has already picked ik, to this particular set again, I1 to Ik minus Ik. Oh, sorry, yeah. N. And also we can denote it by n minus k. So what I want is the remaining n minus 1 agents, they are able to divide the cake, the remaining n minus 1 pieces, in a manner which is again NV free, such that, or proportional, or any fairness notion you are assuming, such that this again happens, Vi of I of pi k of I is greater than equal to Vi of, let's say, Ij for every j, and again for every I in first n minus 1. Yeah. So again, just to parse through the equation which I've written, I'm assuming the notion of NV freeness currently. So I want that remaining agents, when given the piece I of pi ki, which just means that you look at this particular bijection, you see which particular piece he or she is getting. So the valuation for that particular piece for agent I must be at least his valuation for every other piece. Again, note that I am including the piece Ik. He shouldn't be envious of that nth secretive agent also. Okay, it's not he's being out of the system. Then it just reduces to n minus 1 setting. It doesn't make sense. So what I want is, let the secretive guy, so I've already done the division. Let the secretive guy come, pick a piece of his own choice like a boss, and then leave the system. Okay. Now what I want is that there are now remaining n minus 1 pieces in this particular allocation. I want to now somehow allocate these pieces to the remaining of n minus 1 agents such that they are still NV free amongst them, and also not NV free, also not envious of that nth guy, which means which in particular means that whatever they get in this is also at least Vi of Ik. This is the choice of secretive agent. Yeah. Can someone tell me why the secretive agent wouldn't be NV free? Would be NV free? Exactly. He anyway got to pick first. He cannot be NV free, right? He picked the piece. He picked his favorite piece out of all of these n minus 1 n pieces. Yeah. Okay. The definition is clear. Okay. So currently I wrote the definition of secretive NV freeness. Okay. Yeah. I didn't. Is it specifically? I really am not able to hear you. I'm sorry. Can you speak it? Oh yeah. Okay. So yeah, good point. So currently, this is I1 is a disjoint set of intervals. Let's say. Yeah. So it can be somewhere like So this is I1 1 and this is also I1 2. As in, yeah. Just to be sure, I'm not considering a connected cut right now. Yeah, I should have said it. Yeah. So this particular allocation I, it can be it is a disjoint union of intervals, and each piece I1 can be again union of some finite disjoint intervals. Okay. Yeah. Okay. Is the definition clear? Any doubt in the definition? Yeah. So in essence, what we are saying is, in this partial information setting, when we don't have any information about the valuation of the nth, or let's say the last agent, we still want to come up we still want to show at least first the existence of an allocation in which the secretive agent or the nth agent comes in, picks his favorite piece, and then the remaining agents are still able to allocate the remaining n minus 1 pieces in a fair manner. And also to note that they must not be envious of the nth guy as well, although he got to pick first. Although we made the allocation without any knowledge of his valuations. So this is a strong setting, and we will see what happens here. Yeah. Okay, can someone just tell me the definition of when an allocation would be secretive proportional? Yeah, okay. When an allocation or, okay, so an allocation I, again we have n agents, is said to be secretive proportional. Okay. Can someone answer this question? Just recall the definition of proportionality and recall how we are defining secretive fair or secretive envy-free division, and just see how we'll define secretive proportional now. So an allocation would be a secretive proportional allocation if, no, but what comes before that? Say it louder, yeah. No, you can say it. Don't don't be afraid if it's wrong or anything, but just speak up. Okay. Anyone else? If what happens? Okay. If what I want is for every, okay, for every piece ik, and here k can be anything. Okay. What do I want for every piece ik? Just see the definition of secretive envy freeness for every piece, for every choice ik, where k can be anything. So we wanted an existence of a bijection, right? So I want for every piece ik, or for every choice ik, and this choice is of the secretive agent, I want an existence of a bijection. There exists a bijection pi k. Okay, so pi k would be from where to where, this bijection? Yeah, from all agents minus the secretive agent to, yeah, all the remaining pieces, right? So let me just say it's n minus k, by which I just mean the remaining pieces. So these were the pieces, and you remove ik, such that there exists a bijection with what property? Yeah, I want every agent such that he gets, so whatever allocation he gets under this bijection must be, yeah, 1 by n of vi of the whole 0 1. Again, this happens for all I. Yeah. And yeah, in particular, I want Vn of ik also to be at least 1 by n of Vn of 0 1. Right? This is proportionality, like in the secretive setting. Yeah. Is the definition clear? So what I'll do next is I'll show an algorithm which computes a secretive proportional allocation for n agents, for which by which I mean for any n in 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 polynomial time. Yeah. I'll so I'll show an algorithm now. Yeah. So basically I'll show an algorithm which will achieve proportionality for all agents, even in the presence of a secretive nth agent, let's say. Okay. So remember for the case of proportionality, when we have the knowledge of all valuations, we had moving knife algorithm by Dubious-Paynier, which gave us proportionality, right? So here also we will adapt to moving knife algorithm, and we'll see how to adapt it in the secretive setting and again achieve proportionality. Yeah. So in particular, what I'll we'll show okay. So again here I'll show contiguous piece and not like exactly in the way of proportionality. If, via moving knife procedure we had contiguous pieces, right? What was moving knife procedure? So we just move from 0 and move in the left direction, and an agent shouts as soon as he gets 1/n of his 1/n of the value of the whole cake, right? This is first shout and so on, right? That was moving knife procedure. And we made sure that by this particular moving knife procedure, we indeed get proportionality for all agents. So in particular, I'll show contiguous n partition of the cake 0, 1 that does achieve proportionality even under the presence of one secretive agent. Okay. So again, I'll show an algorithm which will run in poly n, and again the algorithm would be similar to a moving knife procedure. Okay. So just to again say that removing knife procedure can be executed in poly time. In poly time under the cut eval query or Robertson web model, which is nothing but cut and eval query setup. Yeah. So just to recall, what was cut query? How did we define the cut query? Yeah. Yeah. So it was defined like cut. We ask this particular query to some particular agent and asks him that, okay, for starting from particular x, just give me a cut such that your valuation for x to y would be alpha times, let's say I'm considering the whole cake right now, but yeah, this was the cut query. And similarly, eval query was just to evaluate what is your valuation for the given piece, let's say xy. Yeah. Okay. So how does the algorithm proceeds? So for each agent, Yeah, okay. So for each agent, which is in the first, I just have anyway access to first n minus 1 agent, so I need to proceed the moving knife procedure only on the first n minus 1 agents, right? But somehow end up with a secretive proportionality even when the secretive guy comes and pick a piece like a boss and goes away. Yeah, okay. So again what I'll do is for each agent, the first n minus 1 of them, I'll query this. So I'll query each agent that okay, make a cut in this particular cake where you get 1/n of your valuation of the whole cake. So it's again exactly similar as moving knife procedure, but yeah, I ask everyone to make this particular cut, right? So again, so what happens is, let's say this is let's say R1, R2, R3 and so on. These are the cuts made by them, first n minus 1 agents, at which, so for this particular segment, V3 of this 0 R3 is equal to 1 by n, right? Because this particular third agent made the cut here, right? So what would be the next natural step? Where do I, these are the markings, right? Where do I make the cut? Where? I'm not able to hear. Yeah, R3, by which I mean the first leftmost cut, right? Yeah. So what you do is you select the first, select let's say agent 1, okay, I'm re-indexing the agents, but let's say agent 1 with this, the smallest cut, or by which I mean that it's the first cut from left. Yeah. So this is basically argmin over all n minus 1 agents and for this particular query. And let's say this is agent 1, it can be any agent, I star or yeah, or let's say I1, but yeah. Okay. So what I'll do is I'll continue the exact same procedure till the end. I'll then remove this particular agent from my account and then I'll again say okay, from, so let's say this was 0 and this was let's say the first cut made by let's say I1. And now I will query for the rest of the remaining cake and I'll query all the agents minus the nth agent obviously and minus this agent I1 as well, right? He's gone from the system. So I'll again query the exact same cut query, which is starting from now R I1 till 1, give me the mark where you'll reach 1/n of your valuation, right? It's exactly like a moving knife procedure. Yeah. So you keep continuing this procedure till all n minus 1 agents have made a cut, right? So continue the same procedure till each of n minus 1 agents have made their cut. Yeah. So what will this give me? This will, you will have n minus 1 cuts on the cake and therefore you'll have an n partition, right? Yeah, okay. So now what I have is 0, 1 and n minus 1 cuts. So these are n minus 1 and therefore this is an n partition. So I have n contiguous pieces and now I need to somehow allocate them and I'll see how to allocate them. So note that it's not the case that agent I1 has gotten this piece. He made the cut, he let's say reserved his piece, but he has not really gotten it yet. Because who will get to choose first? Exactly, the secretive agent, right? So we have just reserved pieces for agents and not yet allocated them. So this, let's say this is, PI1, the piece reserved by the first agent who made the cut, and so on. Yeah. Yeah, so currently I'll call them, okay. Yeah. Oh, no, 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 no. We are not in the burnt, okay, I am sorry, okay. We are not in the burnt cake setting. It was just for the first 2 slides, I believe. That's it. So we have a good cake. We have all those 4 valuation assumptions, that additivity, divisibility, non-negativity, and again normalization. Yeah, I'm sorry if I was not being clear. Yeah. We are out of the burnt cake. We have a good cake. Yeah, okay. So from here I started partial information setting, like with all those 4 assumptions. Like, and in particular Vi of I is indeed positive for all intervals I in 0, 1. Yeah. Yeah. Any other doubt? Yeah, okay. Uh, yeah, okay, so this is my algorithm, but I now need to prove that it is secretive proportional, by which I mean that for every choice here, so I have n partition, for every choice of the secretive agent, I'll still be able to allocate the remaining pieces to the remaining n minus 1 agents in a way that it is proportional for each of them. Okay, yeah. Yeah. So just for the ease of presentation, I'll reindex the agents in the order of their cut. So, so basically agent 1 is the first agent who made the cut, agent 2 and then agent 3 until n minus 1. So this particular piece is reserved by agent 1. This second piece is reserved by agent 2 and till n minus 1, which is reserved by n minus 1. And this particular piece is just the leftover piece. Okay. Any doubts? Okay. Okay. So what basically I need to show here is, let's say the secretive agent comes in like a boss and let's say picked piece P1. Okay, he says I just want this piece P1, and now basically I need to show is how to allocate a piece to agent 1, because his piece is taken away by the secretive agent, right? So therefore in the definition it was like for every choice k made by the secretive agent, I need to again show a bijection, by which I mean that the assignment of the remaining n minus 1 agents among the remaining n minus 1 agents such that it's proportional for all of them. Yeah. Okay. Let's just. Can I wait? PI. Okay, something. Yeah, PI. Yeah. No, so what do I, okay, so PI is gone. What do you do for agent I? You restart the procedure somehow. That's what you're saying? Yes. Yeah, yeah, yeah. Yes, yes. Correct. Okay. Yeah. Okay, no. So again, the definition of secretive proportionality here is the division is already made. You can't make, so this particular n partition is already made and you can't do anything once the secretive agent has made its choice. You can't reshuffle the marks or something. The cake has already been cut. Yeah, you cannot just uncut a cut. So okay, just to recall the definition again of proportionality. So the allocation is made first and then the secretive agent comes in, picks his choice and then we have to reshuffle between the remaining pieces only. You can't uncut a cut in a way. Yeah, so this is the power of this particular result, that the allocation is made prior to the choice of secretive agent, right? Without even knowing the valuation of secretive agent. Yeah. You can't reshuffle the pieces and say that, okay, let me do with the remaining of n minus I agents. No. That's the power of secretive agent. He was given the choice and then you can't really again do anything with the cut already made. Yeah. So, yeah, so I need to do something else, right? I need to show, let's say, where this agent I will go, or let's say we've been calling it K, right? Let's say Pk is the piece taken by the secretive agent, and now I need to show what to do with this particular agent, let's say. But before that, I'll show something else. Okay, so there's an observation. The first observation is Vi of Pi. Do I know something about this particular value? Yeah, this is at least 1 by n, right? This is how the cuts were made. And this is for all of the first n minus 1 agents, right? At least this much I know. Okay, and this Pn is the leftover piece, as we all know. Okay. Okay, also note that Vi of, let's say, Pk. Okay, so for all k less than I. So can you fill up this particular thing? What should I write here? So agent I made the cut at ith position because we have reindexed all the agents in the order of their cuts. Now I know that Vi of Pi is at least 1 by n. What do I know about of Vi of the previous cuts already been made? Exactly, it is less than 1 by n because they did not shout out, right? So for every k less than I, the one coming before, we know at least they are less than 1 by n because they should have shouted out. They didn't, which means that this is true. Okay, again, ties are can be broken arbitrarily. Yeah. Yeah, for every k less than I. So okay, let's draw forget this is Pk. I'm just yeah. So what is happening is, let's say this is P1, this is P2, and let's say somewhere here this is Pi. So he did not shout out here, right? He was not the first guy to shout out because at every cut we chose the leftmost cut, right? The argmin. So here agent 1 was the one who shouted out, which means that in particular, I'm right now focusing on agent I, his valuation for this particular piece must be less than 1 by n, right? His cut on this particular iteration was somewhere here. It was not here, right? Because he was not the argmin. Exactly the same procedure for here. Here also he did not make the first shout. It was agent 2 who did it. Again, in the next one also he was again not the first one. He was the first one only in the iteration I, right? He was the first one who made who shouted at right. Okay, I've got my 1 by n. Again, note that this is inequality in particular, but we can always write greater than equal to. Yeah. So this second inequality is clear, I hope. Less than equal to? No. If even let's say it was equal to, he would have shouted out, right? Yeah, these are like degenerated cases, we are not worrying about them. Yeah. Yeah, so this is because since agent I did not shout out at iteration k. He was not the first one to shout, right? Okay. So here comes the cool part. So therefore I can write this particular inequality which just does the job or does the trick here. So I can write this thing that I'll do the summation. I remember we have additivity. So V of Pk for all k which are greater than I now. Okay. So I've talked about Pi, I've talked about the ones before. What do I know about the remaining or the subsequent cuts? And this will just give me what I need. Okay. Tell me. Say it loudly, there's no need to be afraid. Okay. So what I know here is, okay, I know the whole piece was valued at 1 because of normalization assumption. It can all be rescaled because of divisibility and additivity. Okay, so I know that the whole piece was valued at 1. I know that the ith piece is valued at 1 by n, so I remove that particular thing from consideration because this is valued at 1 by n, these all are valued at less than 1 by n, and I need to know what happens here. This is this particular, what happens what is his valuation for the subsequent pieces. That's okay. So what do I write here? So what all I can remove? So I can remove I minus 1 by n, exactly, right? Yeah. Because of, so yeah, if you sum this up, I will have Vi of Pk, where k is less than I, is at most I minus 1 by n, right? So what is remaining is at least of this much. This is removed at ith because of piece Pi. This is removed for the earlier ones, and this must be the value, his total value remaining for the subsequent cuts must be at least this much. Okay. So just a few. So this is equal to n. Okay. So does it give me some cool observation, this particular inequality? Okay, the hint is everything argument. Okay. So I know that this particular sum is at least n minus I by n, right? Okay. So okay, my claim is there must exist, okay, I should use second page, let me just use. So I have this particular inequality where I know that if you sum over all the pieces coming after his piece, which is Vi of Pk, I will get at least this particular value for the subsequent pieces. Okay. So via averaging argument, what can I guarantee right now? Exactly. There must exist, okay, there exists at least one particular piece, at least one piece pj where j is greater than I mean like in the subsequent pieces there will exist at least one pj such that vi of pj is at least 1 by n, at least 1 by n. Yeah. Why do I have this? Let's say for contradiction I don't have it. So for contradiction, let's say vi of pj is less than 1 by n for all j coming after I, or let's say k, sorry. Let's say this is true. If I just sum it up again, vi of pk for all k's coming after I, what I'll get is less than I minus, less than n minus I by n, right? There are remaining n minus I pieces here, and all of them are less than n minus, all of them are valued at less than n minus 1 by n, and therefore if you just sum it up you'll get this. So in particular there does exist, and this is what we call as an averaging argument. In particular there will exist at least one particular piece pj for this agent I such that he values it again at least at 1 by n, right? Yeah. So in particular he has at least two pieces for him which are valued at 1 by n. One was pi to begin with because he shouted it at iteration I, and the other is I'll just set, okay, so I'll have a function sigma where sigma of I would be j, which just represents that for agent I, pj is the piece which he again values at least at 1 by n. Okay, so for each agent I, there are pieces pi and p of sigma I, such that both of them are valued at least 1 by n. Right? This is clear? Yeah. Also note that the property that sigma I is strictly greater than I, right? Because you found the piece ahead of piece pi, right? Because you found it somewhere here. So you have sigma I is greater than I for all I in n minus 1. So this holds true for any particular agent because we started with an arbitrary agent I in the set n minus 1. Yeah. Okay. So yeah, this observation just gives us the result now. So what will happen is, just think of this sigma as a backup scheme, okay? So what happens is, okay, I don't care if, let's say I am agent I, and the secretive agent comes in and he takes away my piece pi. I don't care, okay, I have a backup piece p sigma I, I'll just go there. But p sigma I would be someone else's. He will go to his backup allocation and so on, and it will give you a proportional allocation since sigma I is greater than I. I'll be formal in a minute. But just think of sigma as a backup scheme. You have two choices at least. Every agent has two choices at least in the allocation in the n partition here, such that they get value of at least 1 by n from both of the pieces. And also because the backup scheme for an agent I always lie ahead of his primary piece pi. This is also very important. Yeah. There's no cycling back. Yeah. Yeah. V of. No, wait. V of. Vn minus 1. Pn. Exactly. Yeah, this is the observation. Because he only has just one piece ahead of him, right? So this will definitely be true. Because for all the pieces before n minus 1, it was all strictly less than 1 by n. For p n minus 1, it's exactly 1 by n. So ahead also it should be whatever the leftover is 1 by n. Yeah. Yeah. No, just say it again. If anyone pick. Who is anyone? Okay. Yeah, sure. Because it's unallocated right now. It's not a primary choice of any agent till n minus 1. Yeah. It was a leftover piece after we've done the moving knife procedure. Yeah. So his observation was in particular for n minus 1th agent. Let's just set I equal to n minus 1 for this particular observation. So he had his primary piece Pn minus 1, which he values at least 1 by n, and there exists one more somewhere ahead of it. You only got one option, it should be and it must be Pn, okay, because sigma I is always greater than I because of this particular inequality. Ahead of what you have cut, there will exist some piece of value at least 1 by n, right? Yeah. So in particular, this is also true. Right? I hope now some idea is being coming to your brains. Okay. Yeah. So again, just a little informally to give you idea what we are doing. So let's say this is P2, this is P3, this is P4, and this is, let's say, P5, the leftover piece, and n is equal to 5. Huh? Yeah. Yes. 2 by n. Yeah. Okay. Yes. Oh no, this is a procedure. You have to be like truthful and you have to follow the procedure. You need to make a cut as soon as you reach 1/nth of your valuation. Yeah, there's no manipulation or strategicness coming here. Yeah. It's a, yes, he knows. No, that's again, again, they're not being strategic or they're not being manipulative right now. I know we've seen a lot in matchings and votings, but right now we're not dealing in the strategic aspect of fair division at all. Yeah, they're being truthful in a way. So let's say just for an example or for an illustration, let's say there are 5 agents in the system, and therefore I just have valuations known for just 4 agents. The 5th guy is being secretive. So the 4 agents make such a cut, and this is a leftover piece which I just call it as P5. So now let's say this particular agent must have a backup scheme, a backup allocation, a backup piece somewhere ahead of it. So let's say this is for agent 1, let's say it's P2. So basically sigma 1 is 2. Okay, let's say for agent 2 it's P4. For agent 3 it's let's say again P4, and for agent 4 we already know it should be P5. Right? So do you see what will happen for any choice of the secretive agent? Let him pick anything, P1, P2, P3, P4, P5. I'll still be able to allocate the remaining of 4 agents in a way that it will be proportional for them, right? So let's say, I don't know, he picks P1. The secretive guy comes in and say, okay, I just like this piece the best. So what will happen is P1 will shift to, so this will be the allocation. We have not really allocated anyway yet. We have not given an assignment. So the final assignment would be secretive agent, which is n, goes to piece P1 because he picked it. Agent 1 will shift over to piece 2. Agent 2 will shift over to piece 4. 4 will shift over to 5, and P3, agent 3 gets his piece P3. No one really took it. P3 was not a backup piece for any agent, right? So just for being clear, let's say secretive agent picks piece P1. So what will be the final allocation? So agent 1 will be allocated to piece P2. Agent Agent 3 will be located piece P3, right? Yeah. Agent 4, oh sorry, agent 2, I should write agent 2 first. Agent 2 will be allocated what piece? Exactly, P4. Agent 3 is, agent 3 is okay, his piece has not been taken away by any other agent, he will just get P3. And agent 4, yeah, since his piece is taken away by someone else, in particular agent 2, he will just get P5. And this is my allocation, and note that it is a proportional allocation, right? For every agent, for secretive agent it anyway is, because he chose to pick first. For the remaining of agents, since I always am allocating an agent either piece Pi or his backup piece P sigma I, I am sure that they all do achieve proportionality. Yeah. Yeah, no. I understand. We are not just being manipulative right now. But then why P4 will do it? Everyone else will also do some manipulations. I don't know. Yeah. 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 In a way also, okay. Yeah. Okay. Yeah. Yeah. Yeah, again, like it's not trivial to see that we'll have strategy proofness over here. We're not dealing with any manipulations currently. We know the valuations, or let's say the agents are being truthful. Okay, just to note that, okay, we need to make sure that no cyclicity will arise in this particular manner, right? It's not the case that no, every person must be able to get something and no cycles form. It's not the case that P2, agent 2 picks P4 and then P4 says no, I'll pick P3 and there's a cycle going on and you're not able to resolve it. So we'll just say that to begin with only there are no cycles anyway because of the property that sigma is greater than I. So you have a sort of what we say as topological ordering. Yeah. Yeah. So just note that in this particular, since we've reindexed the agents, these arrows which denotes the backup piece, they are always ahead of them and therefore you can't circle back. And in particular, if you just, okay, no. If you have this till n minus 1 and then n. So these are agents, they just, yeah, there are their sigma i's and this is always, n minus 1 always goes to n and therefore n is a sink, right? And since we have a sink, there will be no cycles also. Yeah. Since we can, so because of this property, you can induce a topological ordering which is a cyclic and therefore there will be no cycles forming, right? Okay. Yeah. And formally what is happening is, yeah. So formally we need to construct the bijection pi k, right? Remember for every choice k of the secretive agent, we needed to come up with a bijection, right? So pi k, like, okay, so basically for every choice pk here or ik whatever of secretive agent, we need to construct a permutation pi k, but this is quite simple. What you do is yeah, so from if a piece, okay, I should use this. So if a piece k is picked up, you can have a directed path. So a directed path from agent k till n, which is this particular n, and then let's say this directed path denoted by, let's say, sk. So your allocation pi k would be, so you set for all agents who are not on the path, this sk, set it to be I, and then the ones who are on the path sk, you basically shift over them to sigma I. This would be my allocation, this would be my bijection pi k for every choice pk. Yeah. So note that here also, if p1 was the choice of secretive agent, which means that k is equal to 1, I had a path from p1 to p2, p1 to p2 to p4 to p5, right? This was my path from p1 to p5, and p3 was not in the path, and therefore p3 got, agent 3 got his choice p3, and all others got their choice sigma of I. And we have again a cyclicity because of the topological ordering induced by sigma. Yeah. Yeah. I hope this notion of backup scheme or backup allocation is clear to you, right? Yeah. Yeah. Any questions, any doubts? Okay, yeah. So like, so what is our final result? We are basically proving that in a system, so give me a cake division instance. So where you have n agents, you have the cake 0, 1, but you have valuations only for the first n minus 1 agents. That is your input. In such a case, the previous algorithm which I have described, so there does exist an algorithm okay, which outputs an n partition of the cake let's say, yeah, okay, let me just denote by p again because I've been doing it. So n partition, and note that it is contiguous, right? That is again clear since we did a moving knife procedure and we made n minus 1 cuts, and therefore the partition is a contiguous cake cut for the instance. So which outputs an n partition of the cake such that for every choice, so I am again emphasizing, for every choice of the secretive agent pk, where it can be any choice, he can literally pick any piece because he just comes in, picks it and goes away. So for every choice pk, there exists a bijection, and bijection is nothing but the one which I just wrote here, this pi k, right? And we constructed this bijection using the backup scheme sigma. So there exists a bijection pi k which basically goes from all n minus 1 agents to, so this n partition minus the piece picked up by the secretive agent or the nth guy. So there exists a bijection such that such that this pi k induces a proportional allocation, or in other words, pi of vi of pi k I. So this is the piece agent I gets, which is being dictated by the bijection pi k. This is at least 1 by n of the whole valuation, which is 1 only. Yeah, or just let me write it. Such that this happens for all agents in n minus 1, right? So even in the presence of a secretive agent, we are indeed able to come up with a secretive proportional allocation. The way secretive proportional is being defined is exactly this. You do the division first, and then the secretive agent picks his choice, and the remaining agents are able to accommodate themselves in a way that it is still fair. Yeah. Yeah. And again, the runtime of this particular algorithm is poly. Since we are just doing cut-eval queries, and you can analyze how many cut-eval queries we are doing, it will be poly in n. Yeah. That analysis of counting the queries is similar to moving knife procedure, and therefore it runs in polynomial time. Yeah. Okay. So this is clear. So proportionality in a secretive setting is achievable in poly time with a contiguous cake cut, which is a big thing. Okay. So we also have another result, but I will not at all go into the details of it since I am running out of time, but it talks about secretive epsilon NV freeness. So yeah. So in this particular case, the cake cut can be, let's say, not contiguous, and we are in the setting of non-contiguous, because as we have seen, NV freeness is a difficult notion to compute and to achieve. So in that particular case, we are again indeed able to do the whole thing and achieve secretive epsilon NV freeness, and obviously the algorithm is different, it can't be moving knife. But yeah, so in that particular thing, what happens is everything happens, but at the end what you get is P. So this, let's say this allocation now is some I, which can now be a non-continuous division. So every agent again gets a piece which he values for all other pieces minus epsilon, and therefore it's an epsilon NV freeness. Yeah. So the same thing, we are able to come up with an algorithm which first of all computes a division of the cake, might not be contiguous, such that again for every choice made by the secretive agent, we are still able to accommodate the remaining n minus 1 agents in an NV free manner. And again, this J runs over all n, which means that the remaining n minus 1 agents also do not envy the nth agent. Yeah. But here we are able to achieve epsilon NV freeness, again in poly time. Remember the difficulty we had in computing NV freeness in the general model, which was not being secretive. Here it's a partial information setting, and again we are able to achieve epsilon approximate NV freeness in poly time. Yeah. So the proof is entirely different, but yeah, this is one thing you can keep in mind. Yeah. Okay. Any questions? I hope the setting is clear, the secretive or the partial information setting. There's a bunch of work in partial information settings. This is one of the works in the literature.